Okay, chemistry time today. Today, we are talking about chemistry. So let's just write that down real quick. Put this in your notes. I'm sorry, what? I can't want to talk about this. I can't want to talk about this. That was about a different thing. You'll have to look it up on your own time. We're talking... Oh, no. You made a bad noise. Shh. It's okay, enough. What did you... Okay, that worked. Okay, we're talking about chemistry, and we're also going to review, which this should be a review, but we're also reviewing the atom. So, as we talk about chemistry, remind me about what is chemistry. This is from earlier in the year, so this is not even a review from back when you were in physical science. This is a review from like not very long ago. Remind me, what is chemistry? The study of what? I'll give you that little sentence there.
Elements.
No, not just that. Come on. No, come on. Okay, you're getting closer.
I just don't answer.
Thank you, Sage. Good job using your resources.
What did she say?
Shh, lower your voice. Please, someone can say it now.
Chemicals and elements.
Let me ask this question a different...
Atomic ions.
Some of it is that. None of that's wrong. It's just not the whole truth.
Of course you agree.
Okay, the universe, the observable universe, we're going to get out of this question a different way. The observable universe is made of two, broadly speaking, two things. What are the main two things the universe is made out of? You can't, there's a lot of different answers to this. Matter is one of them. And the other one is, okay, maybe, that might be matter, and it might also be a different kind of, okay, that's not, okay, space, yeah, so there are three. Space, because that does exist, right? Space is extremely important. It's a part of the American, or at least the prosperous West idea that this is a blank whiteboard and that this is a smiley face on it. But really, the blank part matters just as much, right? If this was all just black, it wouldn't be a smiley face either. And so, yeah, space does exist, and it really does. It is important. Does it matter? Well, I mean, it is not made of matter, but the fact that it isn't matter means that it is important. So you got me a little bit sidetracked, but yes, space does exist. So the universe, the observable universe, consists of space, matter, and time. There are four things, but no, I mean time might be pretend, first of all, and at best, time is an understanding of the sequence in which things happen. So it doesn't really consist. The universe doesn't consist of time. Time exists within the universe, but let's not. That's you're getting me off track, and you're doing it on purpose at this point. Look at your little face. Okay, so the observable universe is made of space and matter and a third thing. No, because that's a separate little entity.
The universe.
Which I've already had said the universe. Yes. Let's do a flow chart. Let's make a flow chart. You guys love flow charts. The universe. So we're going to start with this. The universe. Tell me, what might the root word of the universe be?
Uni.
Well, okay, yeah, one. It's the one. It's the one. It's the one verse. It's the. Okay, you need. Everyone as a group, you guys need to lock in. You guys need to lock in. We're trying to do something. This video is going to take 400 hours because you won't lock in. The universe, one thing made of three things, and those three things, we've already said. Space, thank you for reminding me. Matter, what's this other thing that really is not actually even what we're talking about today, but you should know this. What's the other thing?
Elements.
Which is matter. Okay, so it's a specific kind of matter, but actually we are going to put that. Thank you. It's something that isn't space and matter. Nope, that's not the kind of hint we're doing. We're not doing that.
Let's play it again.
I think you might be getting close, but someone has already said that, and that's wrong.
I said matter.
People watching this video are going to think that I'm the worst teacher, and they're probably right. This is not the good way to teach, but I want you to give me this. You should know this. You're going to make me cry because this is not. You should know this.
It's like I really do think it's just time.
I really do think we know.
I really do think you know it.
Science.
Don't say that bad word. Science, we could say, is the study of this, the observable universe. I should put that in parentheses up here because one of my strongly held beliefs, although this is not what you hated this class for, is that there are things that exist but are not observable, like love. Oh, that's so cute. That's just my baby dog. That's so cute. But there are things that are not observable, but within the observable universe, the study of that is called science. And then the study of this, I'll give you this one in a second. We'll come back to that. Can you guess what the study of this is called? Come on. No, the study of matter is called?
Scientist. Chemist.
Almost. Come on. Yes. Okay, that was the initial question, and there we've got the linkage. Chemistry, you pipe down. Chemistry is the study of matter. There. We have, at great length, at great pain, I really probably should just start the video over, or at least cut that part and pretend like you guys got it. Chemistry is the study of matter. Now, here, let me play a little magic trick on you. You had this in your possession all along, some of you, not you, Garrett. Show me the front of your book. What is it called? This is a magic trick. No, not that one. Come on. Lock in, Tommy Tiger.
Chemistry.
Okay, and then subtitled, Chemistry, Matter and Change. Because matter and its changes, the study of that is called chemistry. This should not have been that difficult. Here's why. We talked about this last week. Yep, and 2 years ago, and you need to lock in. And it's on the front of your book. So the study of chemistry is called matter. This was not supposed to be 90% of this video, but that's what it is. What's this other guy? Come on.
Just tell us, please.
Change, okay, change due to what? What do we call the change to anything? What's the only thing that causes changes in the universe? There you go. Find a freaking Lee. Energy. I'm interested to see how the captions come out with find a freaking Lee. So this is involved with this, right? The matter and its changes implies energy. So that's it. That is important. We do deal with energy a lot in chemistry. These two things are related, but they are separate. They are in some ways interchangeable. Even they are the same. They're all part of the universe, the one thing. But just like we can't have a smiley face without some space on the whiteboard, we can't have matter without space, and we can't have matter change without energy. And so all these things are interrelated, and so kind of like this. Are these parts of the universe? Sure. And the universe is composed of them, but they are also interconnected together. So within matter, this is where we were actually trying to go with this if you just answered the questions correctly. How else can we categorize matter? So we have one here. You had a subcategory of matter called elements. What are the other subcategories of matter? And why would we talk about this? Because why would we study these subcategories of matter?
Because they're important.
Because they're part of chemistry, and the name of this class is chemistry. So whether that's important to you or not is your own decision, but the class is called chemistry, so we need to talk about it. Elements, what's another one? Someone said it already. Compounds. What other classifications of matter are there?
Science.
Let's try to think of right answers before we just say stuff.
I agree.
Okay, you could actually, let's do this in a different color. You could give a different set of categories of matter, which we might as well talk about now. Solid, liquid, gas, and no.
Oh, the one other thing about vapor.
Thank you, Garrett. You guys are doing rough. I did this in pink. I don't know how you're going to indicate this in your notes. I did this in pink because this is a separate categorization. So just like you could classify human beings based on their skin color or hair color or gender, and you'd have different categories of people within those, you could also do that with matter. So we can classify matter as the different ways that we think of it, but also these different phases of matter. So anyway, back to the things that make up matter. Mixtures. There we go. That's the one I was looking for. And within mixtures, homogeneous, homo meaning same, and heterogeneous, hetero meaning different. And these are different, I shouldn't use that word because I just said it. These are mixtures. Oh, wait. These are depending on whether we can individually identify the pieces. So a homogeneous mixture, an example of that is a solution. This is one we use very often in chemistry. Another one would be an alloy. Heterogeneous mixtures are things where you can tell the parts apart in a sure cookie. I mean, we could give a bajillion examples. Cake pop, yeah, cake pop. S'more. You know, that's actually in there with the desserts because this might as well just say desserts. Okay, so we have mixtures within heterogeneous and homogeneous, and then how up here I'm going to categorize these changes. Within chemistry, there are two main kinds of changes, according to your vocabulary. What kind of main changes do we... Chemical and physical changes. Chemical changes include when a substance is changing. When one substance becomes another substance. That's the definition. I'm not even going to write that because that was your vocab. You should know that. Chemical changes are when one substance becomes another substance. BT dub, these two things, elements and compound, are both called pure substances because they have a fixed ratio. Compounds are chemically bonded, unlike mixtures, which are just mixed. Compounds are chemically bonded with a fixed ratio. And then physical changes are what? Do the compounds change in a physical change? No, the compounds do not change in a physical change. It's the same stuff before and after. It's just in a different physical arrangement. That would be a good way to say it. So the key one to know, this should be review. This should all be review. The key one to know is that when a substance changes state, ice melting, water boiling, the other thing, gasoline evaporating, when those change state, it's still the same stuff, and so that's a physical change, okay? A lot of people get confused and think that's a chemical change. The actual composition has to change for it to be a chemical change.
But is like wood burning chemical?
Wood burning is a chemical change. Because before it was carbohydrates, after it's carbon dioxide and water. And so those are different things, and so that's a a chemical change. No, burning is a chemical change, period. Yeah, if we were to burn Lucas at the stake for his crimes against chemistry, yes, that would be a chemical change. We won't because of laws, but maybe when society breaks down and there are no more laws, that might be one of the things we have on our list. Okay, that'll be something we think about. Now, we have a discussion about how matter is classified. We have actually two ways that matter is classified. What is matter made of?
Solid, liquid, gas, and plasma.
Okay, that's how it's classified. What is matter made of?
Oh, atoms.
Atoms. Elements are individual atoms of one particular kind. Define atom for me in the Greek.
The basic unit.
No, in Greek.
Oh.
Atom comes from... What happened? What happened? No, what happened? I could hear you confabulating. Okay, whatever. A, well, this is alpha, so A, and tomos. A, as you know, like in asexual or abiological means what? Okay, thanks, Ethan. Great job on your med terms, Ethan. It means not. There you go. So like an abiological factor is a factor that does not include biology. Asexual reproduction is reproduction that does not include sexual interface. Tomos, this one is harder to get out of kids, so I'll just tell you it means to cut. It means to cut. And so an atom is that thing which is not cut, which can't be cut. The idea was, philosophically, a man named Democritus, which you will read about in your text, a man named Democritus, who was Greek, thought, as a thought experiment, as a philosophical experiment, he thought, I can cut this whatever cheese in the Greek theory. You know Greek. Parakarlo. He thought this cheese can be cut in half. If I cut that half in half, I have a quarter. If I cut that in half, it's an eighth. How far down can I cut it? At some point, it must be indivisible. It must be that I can't cut it. And he called that idea the atom. And then Aristotle, like a few years later, came along and said, no, everything is made out of earth, fire, air, and water. And people just bought into that for 2,000 years. But then when the fact that matter is composed of individual discrete particles was rediscovered in the 1900s, what they named them, what the man who discovered that, I think it was actually earlier than that, it's probably the late 1800s, what the man who rediscovered that idea named them was atom, after the idea from Democritus. And that man, I should just know it probably, Dalton, I believe. Yes, Dalton. It'll tell me the year here. He lived from 1766 to 1844. 1803. So in 1803, when Dalton rediscovered that matter is composed of individual particles, he called that idea the atom, or he he recoined the term atom. So Dalton's model, when Dalton, with scientific evidence in 1803, discovered that matter is made of individual particles, which he discovered by demonstrating that when chemicals combine, they combine in certain ratios, right? This fixed ratio idea was his evidence that there must be an individual particle at the basic level. And so he renamed it the atom, or he called that particle the atom. So while Democritus came up with the idea of the atom as a thought, Dalton was the first one to apply it to what we now think of as the atom. And then after Dalton's model, I mean, I guess that maybe it's not. I'm trying to think if we absolutely need to go through all the different models, or if we could just spend our time more usefully on something other than that. I don't know. I feel like I rip you off if I don't tell you all the different kinds of the models. That's not nice. You shouldn't have said that. What we'll do instead is you tell me what is an atom made of. So even though Democritus said it could not be broken up and Dalton thought that they were individual particles, what is an atom made of?
Protons, neutrons.
You got it. So an atom can have within it protons, which exist where?
In the middle.
What do we call that?
Nucleus.
Nucleus. And what charge? Hey, lock in, Tommy Tiger. What charge do protons have?
Positive.
Positive charge. And what mass do protons have?
1.
So if we have protons, and if we have, I should do that in a different color. They have a charge of +1 and a mass of 1, and they are located in the nucleus. What about neutrons?
They have a charge of 0, but a mass of 1.
Yeah, and the way you can remember that is that their charge is, in fact, 0, but you could say they have a neutral charge, and they have a mass of 1. And where do those exist?
In the nucleus.
In the nucleus also. And what other thing do we have? Electrons are the other, what we call subatomic particles. These are all called subatomic particles. And what charge do electrons have?
-1.
-1. And what mass do they have? So it's actually I believe 1864th, but let me 1840th. They have a mass of 1 over 1840. So in order even to have them be rounded up, there would have to be 920 of them, and there aren't. There never are in a single atom that many electrons. And so we just, for the kind of math that we're doing with calculating the weight of an atom, we just say they have no mass. So effectively 0. Insignificant. So and where do they exist? I already drew it, but where do they exist?
In the electron cloud.
Yeah, in the electron cloud, or in the orbits, depending on which model you're examining. Like Bohr's model says they orbit. The electron cloud model has them existing in a cloud kind of hazily. The quantum mechanical model has them teleporting, like blipping in and out of existence. And there's truth to all of those, but outside the nucleus in every case. They are not nuclear particles. They are subatomic particles, but not nuclear particles.
So how many of those make up a nucleus of a cell?
Yeah, billions and billions. So the word nucleus as relates to atom and the word nucleus as relates to cell, they're similar in that they both describe the central component of the thing, maybe even just philosophically. Like the nucleus of a cell doesn't have to actually be in the center. But they describe the central component of the thing. But they are not actually related terms, right? While you're right, cell nuclei do have atomic nuclei in them, that's not really the point. That's not how they're related.
So theoretically, if all of our electrons...
Probably hypothetically. Whoa, what could sync possibly mean?
Like they blip all...
Oh, sync, like S-Y and C. Yeah, absolutely. So that's actually one of the fascinating ideas in chemistry is when we look at entropy, it's actually statistical. And so there's nothing but statistics keeping all of your electrons from being on one side of your body at any given time. Like that's totally possible. An electron can exist anywhere in the universe. It's just much more likely to exist in a certain area around the atom. And so is it possible that all of the atoms of oxygen surrounding your head could just instantly go to that side of the room at random and then you would suffocate? Yeah, possible. But like the odds are none. They're I don't know, quadrillions. Yeah. But it's a statistical law.
chance of...
Yeah, you have room for... Yeah, you have some non-zero chance of when you go to hit something, right? When that girl was stepping out with your man, you go to slap her. There's a non-zero chance that your hand goes straight through because all the electrons are out of sync. Yeah, that's absolutely possible. But possible in a non-real sense, like technically possible, but statistically impossible.
So is there a way to make like a teleporter?
No.
No?
Well, not right now. There is actually you're getting me off track and you're doing it on purpose, but there's a kind of interesting idea you can look into called quantum entanglement, where information seems to be able to be teleported, and there's a whole section of computing called quantum computing based on that, which is kind of interesting, but not really the point of this. Now, I do want to tell you here are the maths that we're going to do for this chapter. It's just these are both review. And now I recognize that does not mean you know what you're doing. And so I'm just telling you that's a review. I'm going to give you a couple of examples here, and then you're going to do them for practice on your chapter review. Okay? So are you ready for the kind of math that we're doing? One is we're going to calculate protons, neutrons, and electrons for a given isotope. So let's say we have an isotope of manganese, and we'll call it manganese 55. First of all, manganese 55 we write like that, or we write like this. These are the two ways to write it. This is called standard notation. This is called isotope notation. Top left corner tells us the what? I just told you.
Ions.
No.
Protons.
No. Okay, why don't you try to get it right and then say the answer? Yes, the atomic mass, or what we want to call now the atomic weight. So that 55 is the atomic weight. We use that atomic weight, and we use what else we know about manganese. Found where? Periodic table. So, but listen, by the way, this 55 did not come from the periodic table. That's a given number. That's a whole number because we're talking about one specific isotope. Sage, you need to lock in. We did not get that number by rounding up 54.938. This is a given number. You are given this number. The atomic weight is given. That's part of what makes it this isotope. Every atom in existence has a specific number of protons, neutrons, and electrons, and they are never decimals. What the periodic table shows are an average of all of them. So you guys know how averages work. Even if, let's say, on a test, Lucas gets 100, Garrett gets an 80, and Ethan gets a 70. If we were to add all those up and divide by 3, we very well might get a decimal number, right? They all got whole number scores, but we might get a decimal number as the average. And that's why it's the same thing why these are decimal numbers. It's not because any atom has an atomic weight of 54.938. That's impossible. But some of them have an atomic weight of 55, and some of them have an atomic weight of 54, some of them have an atomic weight of 53, and so when we average them, we end up with decimal numbers. So anyway, this isotope has an atomic weight of 55. How many protons, neutrons, and electrons, and how do we know? Oops, shouldn't put that there. Protons?
One of them always has
Do you remember?
the same weight as...
Yeah, but hey, let's try to think about things and get the right answer and then say it. How many protons and how do you know? That's what I'm looking for.
55.
No.
25.
Yes. 25. And how did you know? Where did you find it?
On a periodic table.
Okay, on the periodic table, where specifically? What is it?
It says it right there.
The top right corner.
Okay, so what is that on the periodic table called?
Proton of the charge.
The number of protons, but it's not called. On the periodic table, that's called the atomic number.
Atomic number.
Okay, so the atomic number is equal to the number of protons. So the number of protons is equal to the atomic number. And again, one last time, where do you find that number?
Top right. In the periodic
On the periodic table. How many neutrons?
5.
You need to stop saying things that are wrong and wait until you have the right answer and then say it.
35.
Nope.
30.
30. Are you just saying random numbers and you happen to get it right? No. How did you do that?
You subtract 25 from 50.
Okay, yep. It's the atomic weight minus the number of protons. The atomic weight. Where did you get atomic weight from? Nope. Nope. The atomic weight was given. It's always given.
Now there is 0 electrons.
Wrong. How many electrons are there?
25. No.
Yep. How do you know?
Yes. Protons always equals electrons.
Yep. Equals the protons unless, yep, unless there's a charge. Good. And how would you know if it's charged? Yeah, I would tell you. Excuse me. Let's do another one because you're bad at them. And hey, it's okay to be bad at things. The first step to being good at something is being bad at it. How do you get better at things?
Try.
Okay, use it. Yeah, that's very rich coming from you, because how do you practice? By doing the work. This is why. Let me tell you, this is not a podcast about educational philosophy. But one thing I really believe is that you only get good at something by doing it, and that's why I assign you this. You think I assign it to you so that you can't go to the football game, you have a miserable life, you can't go out with your girlfriend. You think that I give you this to be mean. I give it to you for the practice. You can't get good at this unless you practice, just like you can't get good at riding a bike or fishing or whatever other crap you like to do unless you practice it. So let's do another one. Let's pretend there's such a thing as cadmium 110. I bet there is. Cadmium 110. So we would write it like that. We don't pronounce this 110 CD. We still pronounce this one cadmium 110. How many protons? Not Garrett, someone else. How many protons? I would love to hear a female voice, but we'll see what happens. And I'd love to, if it is a male voice, I would love it to be right and have thought about it. Yep, you got it. Protons, 48. How many neutrons? How do you know? Wait, first of all, where did you find the number of protons? It's on the periodic table. Good. It's the same as the atomic number. How many neutrons? How many neutrons?
62.
Tell me the math for how many. You're actually right. Never mind. You got it. 62. How did you do that?
I subtracted 48 from 100.
There you go. You subtracted 48 from 110. Good. And then how many electrons? 48. It's the same as protons. Let's do one more of these, and then we're going to call it a day on those. There will be another kind of math though to do. Let's say calcium 40. Let's have it be this, calcium 40, 2 plus. There we go. So we still pronounce it calcium 40. We might say, if we were being specific, we might say calcium 40 ion. Ion, one of your vocab words, means it has a different number of electrons and protons, which gives us a little hint. How many protons, male voice?
Hold on, where is it?
Top left, or top-ish left. Yep, 20 is correct. 20 protons. How many neutrons? This should be fairly easy math, female voice. 20, because 40 minus 20 is 20. Is it because these are always the same? They're demonstrably not always the same. So no, it's because 40 minus 20 happens to also be 20. And how many electrons? Think about it.
20.
Not 20 is exactly right. It's not precisely right, but it is exactly right. How many did you say? 18. Yep. It has fewer electrons than protons. You can tell because it has a positive charge. And we can't change the number of protons because otherwise it wouldn't be calcium. And so we have to reduce the number of electrons. It has only 18 electrons. It has lost 2 electrons. Not really the point of this chapter, but why would it do that? Why would it lose 2 electrons?
So it can be positive.
No?
To share with another
Yeah.
calcium.
Yeah, to become more stable.
Why did calcium have a better day?
Is this a joke?
Yeah.
Okay, why did calcium have a better day?
Because it lost 2
Because
electrons.
it lost 2 electrons. Yeah, we've all been there. Okay.
That's so funny.
No, it's positive.
Okay, another stand by. I need to get an example for this one because these ones exist in reality, and I can't just pull examples out of my head like some people can. But where did they go? Okay. Listen, I'm not talking, so the mic is just picking up what you guys are doing. I don't think you want that.
Oh, no.
Okay, here we go. Uranium-238. This is how we do these. These ones are nuclear decay. Uranium-238 undergoes alpha decay. So you would be given, the problem you would be given is uranium-238 undergoes alpha decay. So this little sign when doing nuclear equations, which is what this is called if you remember from physical science, is called undergoes. So uranium-238 undergoes alpha. Do you remember the symbol for alpha? It already came up once today.
A, right?
Yeah, it's this A. In fact, when I erase, that's the past tense of erase. When I erased the atomos thing from before, that was the letter alpha. So there's the little A, little alpha. So it undergoes alpha decay, and it becomes, well, if you remember, alpha decay, you'll have to look back in your notes for physical science. Alpha decay, in fact, I would just copy that note from physical, or that chart from physical science into your chemistry ones. Also, in previous versions of this video, I have given the chart again, but we just won't have time. So if you want to find that, you can find that on youtube.com. Anyway, alpha particles have a mass of 4. So if this is losing a mass of 4, what is its new mass? 234. 234. And they also have a atomic number of 2. An alpha particle has a mass of 4 and it has 2 protons, or has an atomic number of 2. And so instead of being uranium now, it's going to lose 2 protons, basically. And what will it be now? Thorium. So now it's thorium-234. So uranium-238 undergoes alpha decay, and the daughter product is thorium-234. This is called, give me this thing. This is called the parent isotope. This is called the decay mode, as in like the style of decay, the way it decays. And this is called the daughter, either daughter isotope or the daughter product. Your assignment will include nuclear equations and determining the number of protons, neutrons, and electrons for a given isotope. I have a question for you before you ask me that question. Do you understand, not you, Ami, that this should be review? Right? You at least remember that you did this. I'm not asking that if you can do it perfectly, but you remember that you did it. Do you also, no, it's good. It's good for you. Well, that's on you, dog. It's not my fault you waited this long to take chemistry. If, to the other point of it being a review, I have personally made, and there are also good videos, but I have personally made probably 12 videos explaining how to do both of these in quite a bit more detail. You can watch those if you want. Like I say, they're also good ones. You had a question.
Yeah, why is the list 4 again?
Yeah, so great question. Why does this even happen at all? Why does nuclear decay exist? What's up with uranium-238 that makes it decay? It is what? It's radioactive. It's another way of saying it's unstable. The atom itself is unstable. It falls apart. Big things fall apart. Other questions? That was a good question. Why number 4? Why this? Yeah, that's another great question. I think that's actually a much more difficult question. That would be a good question to do like your doctoral dissertation on. But like, why this specific one? Why does this specific combination of 2 protons and 2 neutrons leave? Other things that can leave are beta particles, which can be either an electron or a positron leaving the nucleus. A positron is a positive electron. It's a piece of antimatter. It's the inverse of an electron. So electron is a negatively charged little baby, and a positron is a positively charged little baby, but it's antimatter. It can also lose gamma radiation, which has no mass and no charge, but it is kind of broken up into those discrete things. Those are the ways it can decay, except for spontaneous fission, which is just, it just falls apart into 2 random other isotopes. That's what happens to you. Other questions? That's not one of them. Other questions about the discussion? Okay.